So the reason why we do this is because I want to change the sign inside here, inside the brackets. So I'm going to take one of these two inside here. I'm going to take ik bar over alpha, common factor, and take I pi. Okay. So if you do this, all I've done is I've taken this guy in here. If you multiply minus I pi with I k bar alpha, it gives you this. Minus I times I is plus pi k bar over alpha. That's what you do here. Okay, and that's minus plus u alpha. In here, just leave it as it is, minus pi k bar over alpha. So now we have the same thing for u, this is for u negative. And now we have the same thing for u negative, the same formal expression. We have u alpha, I k bar over alpha, and that exponential. Good. So now it's not like here that it's 0 in a whole semi-axis and it becomes non-zero. Now we have something which can be analytic. Now, is it analytic? Why? The answer is not simple at all. Okay, let me rephrase it. Does it have any singularities?
Possibly at u equals 0.
Okay, what could it have at u equals 0?
0.
What sort of singularity could it have at u equals 0?
U equals 0. You have t equals 2. You are on the line. You are just on the light cone of someone that's in the origin of coordinate system.
From complex analysis, what type of singularity could you have at u equals 0? Let's forget about light cone, just complex analysis. What type of singularity could it have at u equals 0?
I don't know the answer right now, but it might be related to the fact that the u is there is an I this.
Is this an analytic function?
Yes. What's the definition of analytic?
That it means that powers Taylor's expansion at any point. Is this an analytic function?
Yes.
Any other answers?
Oh, no. Okay.
Why not?
The next, I think that the next term in zero's expansion will be something proportional to 1 over u.
You can't be negative.
Sure, it can be negative. We're in the complex plane.
Well,
What we're looking at complex functions. What type of singularities do you know that they can have? Let me make it easier. If P is an analytic function,
No,
why not?
it blows up at u equals 0.
What sort of what sort of singularity is that? It's a pole. It's a simple pole. It's a pole of order 1. What about this? Sorry? Sorry?
Pole,
Pole, what type of pole?
order 2.
Pole of order 2, good. What about this? What other singularities do complex functions have?
There isn't a pole of order 1/2. There is no pole. There's no singularity.
There's no singularity. There's a branch point here. There's a discontinuity. That u equals branch, u equals is a branch point. Take another one, log u. Well, first of all, it does have values when u is negative, right? As a complex function, this log absolute value of u plus I argument of u. That's how you get it in the complex plane. But it has a pole at u equals, it has a branch point at u equals 0. Why? Because argument of u, you can take any branches you want. Say one branch would be minus pi and pi. One excluded, the other one included. Okay? So that tells you, take u equals 1 so that this equals 0. So take this case, u equals 1 so that log u is equal to 0. Okay? So this guy is gone away. Now what about this? This is the argument. The argument is 0 here, it's log pi over 4 here, pi over half here, 3 pi over 4 here, and it's plus pi as you approach it this way. As you approach it the other way, it's minus pi over 2, it's all continuous, 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 minus pi over 4, minus pi over 2, minus 3 pi over 4, and in here, so it's plus, yeah, this plus pi. Okay, it's plus pi over 2, it's 1. In here it's minus pi over 2, it's pi over 2 here, and down here it's minus pi. So there is a discontinuity on here. That's a branch point. There's branch 1 here. The cut, you can take it anywhere you want. You can take minus pi over 2 to 3 pi over 2 if you wanted to. The branch cut, you can take it in any direction you want. But the branch point is there, and you have to take a branch cut going in any direction, in some direction. You could take argument of u, you could take it between minus pi over 2 or 3 pi over 2, and include one of them. It doesn't matter which one to include. Include this one. So in that case, it would approach minus pi over 2 here, and approach 3 pi over 2 here, so there would be a discontinuity all along here. So again, the branch point, you can't move it, it's at u equals 0, and the branch cut, you can take it, it doesn't matter, you can take whichever direction you want. And that's the same for u equals square root of u. Have you seen this before? Have you done complex analysis?
very, very, very bad one. I congratulations.
This is being recorded, by the way.
No one knows where I'm from.
If you did complex analysis, you must have seen poles.
Yes, but
I have some poles, but not the branch cut.
That's right. You didn't look at the square root. I find it right that hard.
I never described a branch point as a singularity. You asked the kind of singularity I was, well, never saw this like a singularity. There was removable singularities, there was pole singularities, there was essential singularities,
Yeah.
but never branch cut singularities.
I don't know why they would exclude that one. Okay. Branch point u equals 0. So the function is not analytic along the branch cut. Okay, it is analytic everywhere else. It is analytic at this point. You can have a power series expansion at this point that converges, has a non-zero basis of convergence. You can't have it on the branch cut itself. Now, that's true whether this is 1/2 or any power which is not an integer. If this is 3, then that's fine, there's no branch point. But if it is 1/3, branch point. If it's I/3, branch point. If it's I times 0.123, branch point. In here, we have k bar over L, it's a real value, that's generally I times k bar over L over alpha is not, generally it's not an integer. And so this has, there is a branch point at u equals 0. Okay. In which direction is the branch cut going? You know, I'm starting to wonder, like, would it be worth having a complex analysis course in CPF? Like, I thought that in the degree, you guys should have seen this in a degree.
We see this, but there are a lot of issues that can happen.
As Cassie said, if I'm not wrong, as well in my degree course, I don't remember they did analysis or even mention this.
I'm very surprised. The square root is a very important branch point. The square there's about 3-4 times of singularity.
Let me explain what happened. When I was doing the complex analysis course, there was a professor from mathematics that was teaching us, and with a month of the course, he just abandoned the class because he just got a position in some other country, so he just abandoned the class. And a professor from physics, which was not supposed to give this course or anything like that, just filled the hole so that everyone can graduate in the 4 years. So that wasn't happening in my case. It was not a very good course.
Okay, so I mean, you can look at this stuff. You can Google it. You can go to Wikipedia webpage. It's important to know that there's even a Wikipedia webpage, I'm sure, about branch point. Okay, so there's a branch point about u equals 0. Okay, so all you need to know is what I've explained. I don't you need to know a lot more than what I just explained anyway. So in which direction am I taking the branch cut?
I'm confused because
We couldn't just choose.
yes.
Yeah, I've made a choice here. Where is the choice?
It's in the direction.
In the which?
You.
Well, it's in the complex U plane. What does U direction mean? So all this is in the
Separation, like.
all this is in complex. We're in the complex. When we say meaning complex analytic, in the complex U plane. When we say bounded and analytic in the lower U plane, we mean complex U plane. So what does U direction mean? So the argument, the principle,
Over the imaginary axis.
well, typically this goes between minus pi and pi. So really the branch code is here. Now really the question is, are we doing this? Or are we doing this? Branch code is around here. But is it this, which means that would be this? Sorry, yeah, it would be this. Or are we doing this, which means pi included, minus pi not included? Which one of the two are we doing? So the answer to this is in this step, or rather, well, this step or this step. In here, we had minus u inside, alpha is positive. We had minus u inside, this was for u negative. So we were at a point here, minus u, where u is negative and therefore this is positive. We were here. The question is, if we want to go here, is that equal to exponential of plus I pi times minus u? Or is it exponential of minus pi I times minus u? Exponential of minus pi I gives you a phase of minus pi. This gives you a phase of plus pi. So this value here, is it this or is it this? I have written this. Well, it's written on the board.
Pi.
Sorry?
Pi,
Multiplied by minus I pi.
Minus I pi, right? It's written here, and I even put an arrow here to say that this is the answer. So it's minus. We're doing this. Okay. So does this mean we're choosing this or we're choosing this?
Minus pi included.
Minus pi included, exactly. Because minus 1 is exponential of minus pi I, it's this. So the branch code is not here. We allow him to reach minus pi. We're not allowing to reach phase of plus pi. We're allowing to reach a phase of minus pi. So it is this. It's minus pi included, pi excluded. And that's Hawking radiation. That's why the black holes shine. It is this choice that means that it is analytic, this resulting, this function now, with the branch code choice being in the upper U-plane, means that it's analytic in the lower U-plane. And so I'll now prove boundness, that it's bounded in the lower U-plane, but at least it's analytic in the lower U-plane, and therefore this is a positive frequency mode with respect to DDT. Okay? So this exists a branch point as I say, is chosen like this, with a branch cut around here. And so it's analytic in the lower U-plane. Not in the upper U-plane. I still want to show boundedness in the lower U-plane. So write it in polar coordinates with the branch cut taken in the upper plane. And so this is equal to, so now just writing this, alpha u is given by r exponential of I times the phase. Okay, so in here you've got r I k bar over alpha exponential of I theta times this, so this is minus theta k bar over alpha. This is a purely imaginary number, so absolute value of that is equal to 1, and you just have this guy here. Now this is K, this is for yeah, we're doing, I said at the start, we're doing all this for k bar positive. Okay, so you can do all this for k bar negative as well, but we're considering just k bar positive. That's what we, at the start of this, that's what we started doing. Theta plus pi, that's positive, because theta, it's non-negative. And so this is less or equal to 1. And so bounded. You can do, all this was for k positive. You can do the same thing for k bar. U bar, k bar. follows in a similar way. You could try this as an exercise. Also, you want to normalize them. Okay, so again, I'm not going to do this, but I'll show you, I'll indicate how to do it. Well, in fact, there's three. So just trivial from the properties of phi, from the inner product of the phi's, you just get that trivially. So you get so you get n to be equal to this, and this is with a choice of beta of n real. That's just a phase. That's an arbitrary choice of the phase. It does not affect any of the physics. You could choose it in another different way, a different phase for n, and that would give you. You could carry it through, and it wouldn't affect any of the physics. Okay, so we have UK bar R. This for K bar, all K's. So for K bar positive, they're mostly concentrated in R because they're killed by this. And so you can also do the same thing. So this is for the right Wheeler wedge, and you can do a similar thing for the left Wheeler wedge. So I suggest that we, again, try this as an exercise, and again, for K bar positive, they're mostly concentrated in the left Wiener wedge. And so these modes are analytic, unbounded in the lower half U and V planes. So that means that there are combinations of positive frequency modes only. They're just positive frequency Minkowski modes. They're just positive frequency Minkowski modes. This is what we call phi k. We call this phi k. And so there are positive frequency solutions. And so the UK bar R and L define the same Minkowski vacuum as the phi k. Okay, so I'll write it explicitly what I mean by this. You expand the field, you can expand the field in terms of this phi k bar R L. Define a vacuum state which is annihilated by the coefficients, the Fourier mode coefficients in that expansion, and that vacuum state is the same as the Minkowski vacuum state. Okay? As long as they don't include negative frequency modes, the beta coefficients in the probability of transformation are zero, and so one vacuum state does not contain any particles, but the other one doesn't. Any questions? So I haven't finished it. We'll elaborate a little bit more on this. And we'll finish, just in half an hour more or less, 15 minutes to finish on Moore effect. And then we're moving on to course space then. Now I need to recover lectures. 10 lectures. Yes. So we have different options. One option is, at least for next week, that we do 3 hours. Are you okay with that? For next week, and we'll see later on.
We have break.
With a break in the middle, yes.
1 hour just after this.
Yes.
I will not be able to be here for the last hour of the lesson.
Okay. Another option is to do an extra day. Monday at 2.
I think it's better to do it on an extra hour, and then I find I can watch the internet.
Okay. Will you never be able to do the extra hour, or just next week?
I will never be able until December.
Yeah.
I
What about Monday at 2?
can do it on Mondays.
Sorry?
I can do it on Mondays.
So does it suit you next Monday at 2? 2 to 4 p.m. Does it suit you? Does it suit you? Yes. Okay, so next week we'll do Monday and Wednesday at 2. We won't do those every week, but at least we'll catch up. 2 hours. Okay, so we'll see you. I'm going to put on the website which lecture room, hopefully it will be this one, Dr. Campbell, in the website, the lecture website will say which room. Okay? Thank you.
When we will start